America's seasons are no longer changing the way they used to. Winter lingers where spring should begin. Summer heat arrives too early, then stays too long. Autumn fades into warmth, while sudden cold still returns without warning. Across the United States, the old boundaries between the seasons are starting to blur, and scientists say this is not just a strange pattern. It is a real shift with serious consequences for weather, nature, and daily life. This is space science. If this kind of deep climate documentary is meaningful, please like the video, subscribe to the channel, and stay with the story. Earth turns in quiet regularity beneath a steady flow of sunlight. From far above, the planet does not show seasons as lines on a map. It shows them as a moving balance of light and darkness, warmth and cooling, cloud and clear air. America rests within that larger balance. Its fields, forests, deserts, mountains, rivers, and cities all receive energy from the same sun. Yet they do not receive it in the same way at the same time. The changes that people call spring, summer, autumn, and winter begin here, in the broadest setting, before any storm forms and before any local forecast takes shape. The first condition is the shape and motion of Earth itself. Earth is round, so sunlight does not strike every place with equal strength. Near the equator, the sun's energy arrives more directly. Closer to the poles, the same energy spreads across a wider surface and passes through more of the atmosphere. This makes high latitudes cooler on average. America spans a large range of latitude, from tropical waters and subtropical coasts to northern forests and Arctic lands. That wide reach means the country already contains many forms of seasonal experience within one landmass. Even in calm climatic periods, southern Florida, the Great Plains, New England, the desert Southwest, and Alaska do not move through the year in the same manner. The second condition is Earth's tilt. The planet spins on an axis that leans relative to its path around the sun. That lean changes how sunlight falls on each hemisphere over the course of a year. When the northern hemisphere tilts toward the sun, days grow longer there, and the sun climbs higher in the sky. More energy reaches the ground over more hours. When the hemisphere tilts away, days shorten, the sun stays lower, and the surface loses more energy than it gains. This is the basic cause of the seasons. Temperature does not respond instantly, because oceans, soils, ice, and the lower atmosphere store and release heat over time, but the direction is set by the changing angle and duration of sunlight. In this broad planetary sense, seasons are not separate objects that arrive one after another like neat compartments. They are phases in an ongoing flow of energy. One season fades while another builds. At any moment, parts of the Earth system still hold the imprint of the previous season, while other parts respond to the present one. The land often warms and cools faster than the ocean. Snow can preserve cold conditions even as sunlight strengthens. Water can hold summer warmth after daylight begins to weaken. This natural lag means that seasonal boundaries are never perfectly sharp. They are zones of transition. What now appears unsettling in many parts of America is not the existence of overlap itself, but the growing intensity, speed, and irregularity of that overlap. A warmer planet changes the background against which all seasonal patterns unfold. Earth now retains more heat than it once did because human activities have increased the concentration of heat-trapping gases in the atmosphere. These gases allow sunlight to enter and warm the surface, then slow the escape of some of that heat back to space. The added warmth does not spread evenly. Oceans absorb much of it. Land areas tend to warm faster than the sea. High northern latitudes often warm faster than the global average. The result is not a simple, uniform rise in temperature across every place and every month. The result is a changed energy landscape, one in which old seasonal rhythms operate under new conditions. In that changed landscape, America sits in a position of special complexity. It faces two great oceans and the warm waters to the south. It reaches into the middle latitudes, where warm tropical influence and colder polar influence often meet. It includes long coastlines, broad interior plains, high mountain systems, dry basins, humid lowlands, and frozen northern regions. Because of this geography, small shifts in the larger energy balance can produce large shifts in lived weather. The country does not need the fundamental cause of seasons to change in order for seasonal experience to feel altered. Earth still tilts. Earth still circles the sun. Day length still changes in orderly fashion. Yet the atmosphere and oceans through which that solar rhythm moves are warmer than before, and that warmth changes how the rhythm is expressed. From the outermost view, the collision of seasons is therefore not a failure of astronomy. It is not a sign that spring and winter have lost their meaning in a literal sense. It is a sign that the physical system translating solar energy into local weather now carries more heat, more moisture, and in many places more instability than it once did. A winter day can be interrupted by unusual warmth. A spring landscape can be struck by hard cold after early growth begins. Autumn can linger with summer heat, then yield suddenly to freezing air. These events feel like seasons arriving out of order, but they arise within a single connected system whose background state has shifted. Even without moving inward to storms, oceans, or local landscapes, the broad geometry already reveals an important truth. Seasons are not caused by temperature alone. They are caused by the distribution of solar energy over time and space. Temperature, snow, rain, cloud cover, and wind are responses layered on top of that foundation. When the foundation remains the same but the responding system changes, the familiar markers of the seasons begin to move out of step with one another. The calendar may say one thing, the sunlight may suggest another, and the air at the surface may behave in a third way. This is one reason seasonal change can feel confusing. The sky still follows the ancient pattern of tilt and orbit, while the climate system increasingly reshapes how that pattern reaches daily life. Observations across recent decades show that many regions warm earlier in the year, stay warm later, and experience more unusual swings between heat and cold. The exact expression differs by place and season. It also remains uncertain in some cases how strongly a specific short event can be attributed to the warming background rather than to natural variability alone. But the broader signal is clear. The baseline has shifted. The range of likely conditions within each season has shifted with it. The transitions between seasons, once more stable in memory and expectation, now often feel compressed, stretched, or mixed. From the distance of space, none of this appears dramatic. Earth continues to turn. Sunlight continues to move across the hemisphere in measured progression. The continent brightens and darkens, warms and cools, according to laws that remain the same. Yet within that calm order, the stored heat of the modern climate begins to alter the timing, contrast, and texture of the year. America's seasons still arise from the same celestial design, but they now do so in a thicker atmosphere of retained warmth, over oceans that hold more heat, across land that responds more quickly to extremes. The collision begins here, in the widest frame, where the old rhythm remains intact while the medium carrying it slowly changes. Above the turning Earth, the atmosphere does not stand still. It moves in wide bands and loops, guided by sunlight, rotation, pressure, and the contrast between warm and cold regions. These broad motions are called circulation. Circulation means the large-scale movement of air that carries heat and moisture from one part of the world to another. It is one of the main ways the planet smooths out imbalance. Where sunlight is strong, the surface gains more energy. Where sunlight is weak, the surface gains less. Air responds to that uneven heating. It rises in warmer zones, sinks in cooler zones, and flows across long distances between them. From this process come the major wind belts, the zones where storms tend to travel, and the background structure within which America receives its weather. In the tropics, warm air rises often because the surface receives strong sunlight through much of the year. As this air rises, it cools, clouds form, and heavy rain often follows. Higher in the atmosphere, some of that air moves away from the equatorial zone and later sinks in the subtropics. This sinking air is generally drier and more stable. Farther poleward, other circulation patterns take over, shaped by the growing contrast between warmer lower latitudes and colder higher latitudes. None of these belts form perfect rings around the planet. Continents interrupt them, mountains disturb them, oceans feed them with heat and moisture. Still, the basic structure remains. The air does not wander at random. It follows broad paths set by the physics of a rotating planet under uneven sunlight. America lies mainly within the middle latitudes, a region where circulation is especially active and changeable. This is the zone between tropical warmth and polar cold. Here, the atmosphere often acts less like a settled layer and more like a moving boundary field. Air masses of different temperature and moisture content meet, separate, and meet again. Storm systems commonly form along these contrasts. This is why much of the United States experiences large shifts from one day to the next, compared with many tropical regions, where seasonal temperature changes are often smaller. The middle latitudes are a place of exchange. Warmth moves poleward. Cold air sometimes spills equatorward. Moisture is gathered, lifted, and spread. The seasons are therefore not only a matter of changing sunlight at the ground, they are also a matter of how the moving atmosphere redistributes that energy. When the climate warms, this circulation does not simply speed up in a smooth and uniform way. It changes in pattern, contrast, and persistence. One important feature is that the Arctic, in many observations, warms faster than the global average. This does not erase winter cold, but it reduces the average temperature difference between the far north and some regions to the south, especially during certain times of year. That temperature difference helps shape the movement of the atmosphere. When the contrast changes, the flow above it can also change. Scientists continue to study exactly how much of the recent behavior of large-scale circulation follows from Arctic warming alone, and how much arises from tropical influences, ocean patterns, and natural variability. What is clear is that the atmosphere is responding to a changed heat distribution, and that response affects the rhythm of American seasons. A circulation pattern does more than determine average conditions. It influences whether weather systems keep moving or whether they stall. A moving pattern tends to carry heat, cold, and rain onward. A stalled pattern allows one set of conditions to remain over a place for longer. Under a warm spell, stalling can deepen heat and drying. Under a wet pattern, it can lengthen rainfall and flooding risk. Under a cold setup, it can preserve snow and ice or prolong chill after the calendar has advanced. In older seasonal memory, transitions often seem gradual because the atmosphere more often alternates in moderate, familiar ways. In recent decades, many regions experience longer holds and sharper swings. This can make one season feel as though it presses into another rather than yielding to it. The circulation that affects America is also linked to distant regions. Air over the Pacific can influence western North America before moving inland. Conditions in the tropical Pacific and Atlantic can alter rainfall, temperature, and storm behavior across the continent. Snow cover and sea ice farther north can affect how heat is exchanged between surface and air. This does not mean that every local event has a single remote cause. It means the atmosphere is connected across great distances. America's seasonal experience depends partly on what surrounds it, and partly on what arrives from afar. What seems like a sudden local collision between spring warmth and winter cold often belongs to a much larger arrangement of moving air that spans ocean basins and polar regions. In this broad atmospheric setting, the old idea of one season ending cleanly before another begins becomes harder to sustain. Circulation works through gradients, not walls. A gradient is a gradual change across distance, such as a transition from warm air to cold air. The middle latitudes are filled with such gradients. When they sharpen, the atmosphere becomes more active. When they stretch or bend, different seasonal signals can occupy neighboring regions at the same time. One part of America may sit under unusual heat, while another remains locked in late cold. One coast may feel like early summer, while the interior still behaves like winter. These contrasts are not new in principle, but a warmer and more moisture-laden atmosphere can intensify them and make them feel less stable. The large circulation also helps explain why seasonal change can become uneven across the same country. Spring does not advance northward like a smooth curtain. Cold air can still move southward behind it. Summer warmth does not arrive evenly across mountain ranges, coastlines, plains, and forests. Autumn cooling can be slowed in one region and accelerated in another, because circulation organizes the delivery of air masses. It shapes where the broad solar rhythm becomes delayed, amplified, or interrupted. In this sense, the atmosphere acts as a translator between planetary energy and lived experience. If the translator changes its habits, the message at the surface changes even though the sun and the tilted Earth continue their steady work. Observations indicate that the atmosphere now carries more energy and more water vapor than it did in the past. This supports heavier rainfall in many conditions and shifts the balance of heat between surface and sky. It also influences pressure patterns and cloud formation. It remains uncertain whether every recent meander or blockage in circulation is becoming more common for the same reasons in all seasons and all regions. The system is large, and several forces operate at once. Yet the broad picture holds. America's seasons unfold inside moving belts of air that are being reshaped by a warming world. The collisions that people notice at the ground begin higher and wider, in the restless circulation that gathers contrasts and carries them across a continent. From this outer atmospheric region, the seasons already appear less like fixed rooms and more like overlapping currents. The year turns as it always does, but the air that distributes its effects grows more variable in texture and more capable of holding extremes close together. The continent below receives not just sunlight, but the constantly rearranged outcome of planetary motion, warming oceans, shifting temperature gradients, and a circulation system that never truly rests. Within that moving framework, America's seasons begin to lean into one another, not because the cycle disappears, but because the air between sky and ground now carries its differences in a more unsettled way. High above the continent, within the middle latitudes, a narrow band of strong wind circles the hemisphere from west to east. This flow is called the jet stream. It is not a single smooth ribbon, and it does not stay in one fixed position. It shifts north and south, strengthens and weakens. bends into broad curves, and sometimes divides into separate branches. Yet it remains one of the clearest atmospheric boundaries shaping life below. Along its general path, warm air and cold air often meet. To the south, milder or hotter air tends to gather. To the north, colder air is more likely to hold. The jet stream does not create all weather, but it helps guide the systems that bring weather to the ground. In America, where large temperature contrasts often exist across great open distances, this upper river of air becomes one of the main organizers of seasonal feeling. A useful way to understand the jet stream is to see it as the atmosphere's response to contrast. Where strong differences in temperature exist across latitude, pressure surfaces tilt with height. Air begins to accelerate along those gradients, and because Earth rotates, that movement is turned into a fast west-to-east flow. The result is a current of high-altitude wind that traces the zone between warmer and colder air masses. It is strongest when the contrast is strong, especially in the colder half of the year. Even when unseen from the ground, it influences the movement of storms, the position of fronts, and the extent to which cold air can spill southward or warm air can surge northward. Across North America, the jet stream rarely runs straight. It forms waves. Some waves are gentle, and some become deep. A northward bulge allows warmer air to move farther toward the pole beneath it. A southward dip allows colder air to move farther toward the equator. Meteorologists often speak of ridges and troughs. A ridge is the northward arch associated with warmer, often calmer conditions beneath. A trough is the southward dip often associated with cooler, more unsettled conditions beneath. These shapes matter because they decide where one seasonal character extends beyond its usual reach. When a ridge becomes strong, summer-like heat can enter places that would otherwise be mild. When a trough deepens, winter-like chill can arrive far south of where many expect it. In a more stable pattern, these waves move along. Warmth arrives, then passes. Cold follows, then retreats. Rain falls, then the sky clears. Transitional seasons still contain contrast, but the contrast migrates with some regularity. What has drawn growing attention is the tendency for some wave patterns to become more amplified or more persistent for stretches of time. An amplified wave is one with larger north and south bends. A persistent wave is one that changes slowly, allowing the same general conditions to remain in place. Under such patterns, one part of America can remain trapped under unusual warmth, while another stays beneath repeated surges of cold. The boundary between seasonal states becomes less like a marching line and more like a bent and lingering frontier. This matters because the jet stream is not only a marker between air masses, it is a guide rail for storm development. Surface low-pressure systems often form and move in relation to the upper flow. Where the jet stream curves and accelerates, it can support rising air below, helping storms grow. Where it bends differently, it can favor sinking air and quieter weather. As a result, the position of the jet stream helps determine whether a region experiences repeated storms, extended dryness, sharp temperature swings, or long quiet spells. When the flow meanders strongly, the continent can hold several seasonal moods at once. Snow and freezing rain may continue on one side of the boundary, while severe thunderstorms break out on the other. Early bloom may appear in one region while another remains locked under late-season frost. In this way, the jet stream helps create the feeling that seasons are colliding. The collision is not a physical crash. It is the tightening of contrast across space and time. Warm and cold air masses, each carrying the imprint of a different seasonal regime, are drawn close together by the shape of the upper flow. A sharp front at the surface may form beneath this contrast. A front is the zone where different air masses meet. It is often narrow compared with the air masses on either side. On one side, a person may stand in humid warmth under strong sunshine. A short distance away, another may stand beneath cold cloud and wind. The line between them can shift quickly, then stall, then return. This is one reason a single week can feel like several seasons layered together. Scientists continue to examine how the changing climate influences the jet stream in detail. Observations indicate that the behavior of the upper flow is shaped by several interacting forces, including warming in the Arctic, tropical heating, sea surface temperature patterns, land surface changes, and natural atmospheric variability. It remains uncertain how strongly each force contributes to every kind of waviness or blockage in every season. The atmosphere is not governed by one lever alone. Still, there is broad agreement that as the distribution of heat changes across the planet, the structure and behavior of the large-scale flow can change as well. For America, this means the jet stream increasingly operates in a background climate that is warmer, moister, and in some settings more favorable to prolonged extremes. The seasonal consequences become visible at the ground in familiar yet unsettling ways. Winter air can plunge southward deep into a landscape already stirred by stronger spring sunlight. Summer heat can surge early into regions where soil moisture and vegetation still reflect a cooler season. Autumn warmth can linger under a broad ridge while nearby regions experience sudden polar intrusions. Because the jet stream often divides these conditions, its curves become the invisible handwriting behind abrupt transitions. It explains why a map can show snow, tornadoes, wildfire danger, and near-record warmth across different parts of the country at the same time. The continent is large enough to contain many realities, and the jet stream is one of the main reasons those realities can sit side by side. Seen from this upper region, America's seasonal disorder does not appear as chaos without structure. It appears as structure under strain. The boundary between warm and cold remains organized, but it bends, stalls, and sharpens in ways that bring unlike conditions into closer contact. The old expectation of a gradual handoff from one season to the next gives way to a more uneven exchange. The jet stream, always restless, now often seems to write a rougher script across the sky. Beneath it, spring can be interrupted by winter, autumn can borrow from summer, and calm transitions can be replaced by sudden reversals. The collision takes shape here, along the wavering line where the atmosphere sorts the continent into shifting zones of heat and cold. Beyond the continent, on both sides of it and along its southern edge, vast bodies of water hold and move heat with a patience that land does not possess. The Pacific, the Atlantic, and the Gulf shape America long before clouds gather over a city or wind crosses a field. Water warms slowly and cools slowly. It absorbs sunlight over depth, mixes heat through motion, and releases that heat back to the air over long periods. Because of this, the oceans act as a memory within the climate system. They remember warmth after summer light has begun to fade. They remember coolness after spring light has already grown strong. America's seasons, though often described through land and sky, are constantly adjusted by this slower, larger storehouse of energy that surrounds the country. The eastern Pacific influences the western edge of North America with air that often begins over cool or mild ocean surfaces. Along much of the west coast, especially in summer, the nearby Pacific helps restrain extreme heat close to shore. Marine air, meaning air shaped by the sea, often arrives cooler and more humid than inland air. This is one reason coastal climates commonly feel less severe in their seasonal swings than the interior. Yet the ocean is not a fixed background. Sea surface temperatures vary from year to year and from decade to decade. Winds change the upwelling of cold water along coasts. Upwelling means the rise of deeper, colder water toward the surface. When upwelling is strong, surface waters cool and the air above them changes as well. When it weakens, the coastal ocean can become warmer than expected, changing fog, cloud, and shoreline temperatures. Farther west across the Pacific, tropical conditions also matter. Variations in tropical Pacific water temperatures can reorganize atmospheric patterns over great distances. This process does not operate as a simple switch, and its effects differ by season and region. But it can alter storm paths, rainfall, and winter temperature patterns across the United States. Some years favor a wetter southern tier and milder conditions in parts of the north. Other years favor different outcomes. These recurring ocean atmosphere patterns have long been part of natural climate variability. What changes in a warming world is the background state in which they operate. When ocean surfaces are warmer overall, the air above them begins from a higher energy level. Old patterns can still occur, but their consequences may be expressed through heavier rainfall, warmer nights, or greater moisture transport than in the past. On the eastern side of the continent, the Atlantic carries its own influence. The western Atlantic, including the waters off the southeastern United States, has shown notable warming in many observations. Warm ocean water does not merely warm the air above by contact, it also increases evaporation. Evaporation is the process by which liquid water becomes water vapor in the air. When the ocean surface is warmer, more water can enter the atmosphere, provided winds and other conditions allow it. This added moisture can feed clouds, coastal storms, and humid air masses that move inland. Along the east coast, a warmer nearby Atlantic can therefore blur seasonal expectations. Autumn may stay milder for longer. Winter air arriving over warm water can gather moisture and later produce heavier precipitation. Spring can begin with air that already carries unusual warmth and humidity. To the south lies the Gulf, a compact but powerful source of heat and moisture. Its influence reaches far beyond its shoreline. Air flowing northward from the Gulf often carries warmth and abundant water vapor deep into the interior of the United States. This is especially important in spring and summer, when the contrast between Gulf air and cooler continental air can help drive thunderstorms and sharp fronts. The Gulf has warmed over time, and marine heat waves. Periods of unusually high ocean temperature have drawn increasing attention. Such warmth does not guarantee a specific storm on a specific day, but it changes the reservoir from which the atmosphere draws. When warm Gulf air moves northward into a landscape that still carries remnants of winter cold, the sense of seasonal collision becomes vivid. Moist heat rises over cool ground. Storm energy builds. The calm sequence of spring can give way to abrupt extremes. Because oceans store heat, they also shift the timing of seasons. Land responds quickly to sunlight. Ocean water responds slowly. This mismatch creates coastal lags and inland contrasts. In autumn, the sea can continue releasing summer heat, delaying cooling near shore and softening the first advance of cold air. In spring, cold ocean surfaces can hold back coastal warming even while the interior heats rapidly. This means America can experience several seasonal clocks at once. A shoreline may remain under cool marine influence while inland valleys begin to feel almost summery. Later in the year, the reverse may occur, with coastal warmth lingering after interior regions begin to cool. These differences are natural, But when the oceans themselves warm, the lags and contrast can deepen or shift, making seasonal boundaries feel less familiar. Ocean heat also matters below the surface. The sea is not heated only at its skin. Winds mix the upper layers. Currents transport warmth horizontally and vertically. A storm passing over warm water can draw energy from more than a thin surface film if that warmth extends deeper down. This is one reason sustained ocean heat matters so much to the atmosphere. It creates persistence. A brief cool spell in the air does not immediately erase stored marine warmth. The water continues to influence the air mass that passes over it. In this way, the oceans can support repeated episodes of unusual warmth or moisture delivery, even when the weather above changes from day to day. For America, the practical meaning is simple even if the physics is large. The continent does not experience seasons in isolation from the surrounding seas. It receives moderated air from cool waters, humid air from warm waters, and storm tracks reshaped by temperature differences across entire ocean basins. When those waters warm, the air arriving from them is altered before it reaches the land. A winter coast can feel softer than expected. A spring boundary can become more unstable. An autumn shoreline can hold summer far into the calendar. What people experience as seasons running together often begins offshore, where the ocean quietly retains heat long after the sun's angle has changed. Observations clearly show that the oceans have absorbed most of the excess heat added to the climate system in recent decades. That heat does not remain hidden from weather. It enters the atmosphere through evaporation, turbulent exchange, and the slow release of stored warmth. It remains uncertain how each regional ocean pattern will interact with every future season in every part of America. Ocean circulation is complex, and natural variability remains important. But the broad direction is well understood. Warmer seas make it easier for the atmosphere to carry warmth and moisture into the continent. They stretch the memory of summer, soften the grip of winter in some places, and intensify the meeting of unlike air masses in others. From this oceanic region, America's colliding seasons no longer look like a purely continental story. The land receives the drama, but the surrounding waters prepare much of it. Offshore, energy gathers slowly and quietly. Then it travels inland in marine air, in humid flow from the south, in altered storm paths, and in delayed cooling that reshapes the seasonal edge. The sea does not hurry, yet its stored warmth reaches deep into the calendar. In that patient reservoir, one of the strongest forces behind the mingling of America's seasons takes form. Above the land and sea, between the broad circulation and the weather felt on the skin, the atmosphere carries an invisible burden of water. This burden is always changing. Some of it appears as cloud, fog, rain, snow, or frost. Much of it remains unseen as water vapor, the gaseous form of water mixed through the air. Water vapor is one of the quiet substances that shape nearly every season. It stores energy, feeds clouds, softens some temperature swings, and sharpens others. It influences how heat is felt, how storms grow, and how quickly rain or snow can form. In a warming climate, one of the clearest physical changes is that the atmosphere can hold more water vapor than before. This simple fact has wide effects, and in America it helps turn seasonal transitions into more crowded and unstable passages. Warm air can hold more water vapor than cold air. This does not mean that every warm day is humid or that every cold day is dry. It means that the capacity of the air increases as temperature rises. If moisture is available from oceans, lakes, soils, vegetation, or melting snow, a warmer atmosphere can take up more of it. This matters because water vapor is not passive. When moist air rises and cools, some of that vapor condenses into tiny liquid droplets or ice crystals. Condensation is the process by which water vapor becomes liquid water. In that change, heat is released into the surrounding air. This released heat can strengthen rising motion, deepen clouds, and add power to storms. Moisture is therefore both a substance and a source of atmospheric energy. Across America, the amount and timing of moisture in the air help distinguish one season from another. Winter often brings drier air in cold continental regions, though coasts and storm tracks can still support heavy precipitation. Spring often marks a return of stronger evaporation, moist southerly flow, and increasing cloud growth. Summer commonly carries the greatest atmospheric moisture in many regions, especially east of the Rocky Mountains and along southern coasts. Autumn can remain humid near warm water even as daylight weakens. These are long, familiar patterns, but they are now unfolding in warmer conditions. The atmosphere begins many events with more moisture available than the same pattern would once have held. This makes the character of transitions different even when the broad seasonal path remains recognizable. One of the clearest effects appears in rainfall. When the atmosphere contains more water vapor, storms can produce heavier downpours if the conditions for rising air are present. Observations indicate that intense precipitation events have increased in many parts of the United States, though not in the same way everywhere and not in every season. A warmer atmosphere does not create rain by itself. Air still must rise, cool, and condense. But when that happens, there is often more water available to fall. This means that a spring storm moving through a landscape still touched by winter can bring not a gentle handoff between seasons, but a more forceful release of rain, melting, runoff, and local flooding. The air no longer merely marks the transition, it intensifies it. Moisture also changes how warmth is experienced. Dry air allows water to evaporate from skin more easily, which can help cool the body. Humid air slows that evaporation. In summer, this makes heat feel heavier and more stressful. In the shoulder seasons, when days of unusual warmth arrive early or persist late, high humidity can make those days feel even more out of place. A spring heat surge drawn northward from the Gulf does not only raise temperature, it changes the texture of the air. The atmosphere begins to feel like a different season before the landscape. Daylight, or biological rhythms have fully caught up. This is one of the quiet ways seasons seem to collide. The thermometer shifts, but so does the body's sense of what kind of season is present. Clouds are another expression of atmospheric moisture. They reflect some sunlight back to space, absorb and emit heat, and regulate how quickly the surface warms by day or cools by night. Low clouds can keep daytime temperatures down. Night clouds can trap outgoing heat and keep temperatures milder. When moisture patterns change, cloud patterns can change as well. This does not happen in one simple direction. Some regions may see longer dry spells between rain events, while individual storms become wetter. Some coasts may hold marine cloud and fog differently as sea temperatures shift. Some inland regions may see spring skies fluctuate more sharply between humid cloud cover and dry, clear intervals. The effect is not only on rainfall totals, but on the timing and pacing of seasonal feel. Snow is deeply influenced by moisture, yet it responds to temperature with great sensitivity. A storm in cold enough air can deliver heavy snow if abundant moisture is present. Slight warming can turn that same event toward rain, sleet, or a mix, near the freezing point. A very small temperature difference can decide the form of precipitation. This is one reason a warmer atmosphere can produce confusing seasonal scenes. More moisture may support intense precipitation, while temperatures hover near the boundary between winter and spring conditions. One place receives heavy wet snow, another nearby receives cold rain. A later shift in wind changes both. The result is not the disappearance of winter weather, but a more unstable border around it. Moisture deepens the event while warming complicates its form. The land surface adds to this story. Wet soils and growing plants return water to the atmosphere through evaporation and transpiration. Transpiration is the release of water vapor by plants. Together, these processes increase local humidity and can help feed afternoon cloud growth and storms. If spring warmth arrives early, plants may begin active growth sooner in some regions, adding moisture to the lower air. Yet a later cold intrusion can still damage that growth. In this way, the moist atmosphere and the living surface become briefly misaligned. The air behaves like a later season while the risk of an earlier season remains. The collision is not only between warm and cold, it is between moisture, temperature, and timing. There is also a slower background effect. Water vapor itself is a heat-trapping gas. As the atmosphere warms and holds more moisture, this can amplify warming further, though the initial increase is driven mainly by other human-produced greenhouse gases. This added vapor does not act alone, and it does not increase without limit. It responds to temperature, circulation, cloud formation, and regional moisture supply. Still, it is part of the reason warm periods can become warmer and nights can remain milder, especially in humid regions. In seasonal terms, this can reduce the clarity of cool intervals that once separated one phase of the year from another. Scientists are confident that a warmer atmosphere generally holds more water vapor, and that this contributes to heavier precipitation in many settings. It remains uncertain how local humidity, cloud cover, and storm timing will evolve in every American region, because circulation, ocean influence, land use, and topography all play a part, but the broad physical direction is clear. The sky now carries more moisture potential than it once did. When lifted, it can release more water. When warmed, it can feel more oppressive. When temperatures hover near a seasonal threshold, it can help turn that threshold into a place of rapid reversal. From this moist inner layer of the atmosphere, America's colliding seasons begin to feel heavier and less distinct. The air itself stores part of the change. It carries more water from warm oceans, wet soils, and thawing landscapes. It feeds clouds that dim the day and rain that overwhelms dry ground. It complicates snow, thickens heat, and softens cold nights that might once have marked a clean seasonal turn. In this region of vapor, cloud, and condensation, the year no longer shifts only by temperature and sunlight. It shifts through the added weight of water held aloft, waiting for the moment when rising air turns it into weather. Across the middle latitudes, the atmosphere rarely delivers weather in place. It sends weather along paths. These paths are the common routes taken by low-pressure systems, fronts, and bands of cloud and precipitation as they move across a region. Meteorologists call these routes storm tracks. A storm track is not a painted line in the sky. It is a corridor favoured by the larger flow of air above. The contrast between air masses below and the arrangement of ocean and land across the surface. In America, storm tracks are among the most important structures shaping the lived meaning of the seasons. They decide where rain arrives, where snow forms, where cold air deepens, where warmth is pulled northward, and where one seasonal pattern presses into another. When these tracks shift, strengthen, weaken, or stall, the sequence of the year begins to feel unsettled. In a familiar climatic rhythm, storm tracks migrate through the year. During the colder months, The strongest contrast between warm and cold air often lies farther south, and more active storm routes commonly affect the southern and central parts of the country. In warmer months, the main belt of upper-level activity often retreats poleward, while local heating, humidity, and regional circulations begin to dominate more of the weather. Transitional seasons occupy the in-between period. In spring, the atmosphere may still support late cold intrusions and broad frontal systems, yet increasing sunlight and growing moisture also support thunderstorms and early heat. In autumn, summer warmth may remain in the south, and near warm water while stronger cold systems begin to return from the north and west. These shifting storm paths are one of the reasons spring and autumn have always been seasons of contrast. In recent decades, that contrast often appears sharper, wetter, or more prolonged. A storm track can shift in latitude. This means the corridor of frequent storms moves northward or southward from its usual position. Such a change affects which regions receive repeated rain, snow, or cloud cover, and which remain dry or warm. If a winter track stays farther north than expected for a time, parts of the southern United States may remain unusually mild and dry, while colder and stormier conditions persist elsewhere. If the track dips southward in spring, cold air and storm systems can continue reaching places that have already begun seasonal warming. The result is not merely a delay in the calendar sense, it is a mixing of signals. Trees may leaf out, insects may emerge, and then a strong late-season system may return the atmosphere to a colder state. The storm path becomes the channel through which one season re-enters another. A storm track can also change in intensity. When the contrast between air masses is strong and the upper atmosphere supports growth, storms may deepen more rapidly or carry greater moisture. Stronger storms can produce heavier precipitation, sharper wind shifts, and larger temperature changes in a short period. This does not mean every storm becomes extreme. It means the atmosphere, under favorable conditions, can express greater energy in a warmer climate. This matters because storms often draw upon air that contains more water vapor than before. The path remains similar in a broad sense, but the weather delivered along it can become more forceful. A spring system moving across the central United States may bring snow on its colder side, severe thunderstorms on its warmer side, and flooding rain where moisture gathers longest. This is one of the clearest ways seasonal overlap becomes visible on the ground. Several seasonal modes exist within one organized event. There is another change that affects how people experience the year. Some storm tracks become less progressive, meaning the weather systems along them move more slowly or repeat over the same region. When a track stalls, a place can receive several rounds of rain in close succession. When a blocking ridge nearby diverts systems, another place may receive very little rain at all. Blocking means a large, persistent, high-pressure pattern that slows or redirects the usual movement of weather systems. Under such conditions, seasonal change may stop feeling gradual. It may feel trapped. A region remains locked in cool cloud and rain while another sits under prolonged heat and sunshine. The boundary between them does not move on schedule, it holds. Then, when it finally shifts, it may do so abruptly. One season seems not to fade into the next, but to be displaced by it. America's geography makes these shifting tracks especially important. The western mountains, the open plains, the Great Lakes, the Gulf, and the Atlantic coast all influence how storms form and move. Systems arriving from the Pacific may weaken, split, or reorganize as they encounter mountain ranges. Storms crossing the plains may intensify as they meet warm, moist air flowing northward from the Gulf. Coastal storms can deepen rapidly where cold continental air meets the relatively warm western Atlantic. These regional influences do not erase the large-scale track, they modify it. They make the same broad atmospheric pattern produce different seasonal consequences in different places. This is why one part of the country may experience repeated spring floods, while another endures dry heat and wildfire danger during the same stretch of time. The collision of seasons becomes especially evident when storm tracks align with strong thermal contrasts. A thermal contrast is a difference in temperature across space. Along such contrasts, fronts sharpen, precipitation type changes over short distances, wind direction shifts quickly. One side of a storm path may remain in cold air suitable for snow or ice, while the other side receives warm rain and thunder. In autumn and spring, when the atmosphere often hovers near the boundary between colder and warmer regimes, small shifts in the track can produce very different outcomes. A storm taking a slightly more northerly path may pull warm air far inland and delay frost. A slightly more southerly path may draw in cold air and produce an early freeze or heavy wet snow. This sensitivity gives transitional seasons their volatility. In a warmer and moister climate, the volatility can carry greater impact. Observations across the United States indicate changes in precipitation patterns, the frequency of heavy rainfall events, and the timing of some seasonal storm behavior. Some regions have seen wetter conditions in certain seasons and stronger downpours, while others have experienced more persistent dryness between events. Scientists continue to study how much of the changing behavior of storm tracks arises from warming oceans, altered temperature gradients, natural climate variability, and shifting land surface conditions. It remains uncertain how every regional storm corridor will evolve in coming decades. Yet it is well supported that the environment through which these tracks move now holds more heat and moisture, and that this changes what storms can do once they form. The practical effect is a growing mismatch between expectation and experience. People remember one season arriving with a certain pace, a certain texture of rain, cloud, wind, and cooling. Increasingly, the atmosphere delivers something less orderly. A winter storm arrives with rain at first, then snow, then rapid melting. A spring system brings midsummer humidity ahead of it and lingering cold behind it. An autumn sequence swings from dry heat to flood-producing rain and then to frost in quick succession. The storm track is not just carrying weather, it is carrying competing seasonal signatures through the same week, sometimes through the same day. From this region of moving systems and shifting corridors, America's colliding seasons take on a clear physical form. The year is translated into repeated pathways across the sky. When those pathways move, stall, or intensify under a warmer atmosphere, the handoff between seasonal states becomes rougher. Rain bands, snow shields, cold fronts, and warm surges pass not as isolated events, but as organized expressions of a changing climate system. The tracks remain, but the patterns they carry are more crowded with contrast. In those crowded corridors, winter can linger within spring, summer can spill into autumn, and the continent can feel several seasons at once. Across North America, one of the sharpest lines in the atmosphere is the meeting place between air from the far north and air from the lower latitudes. This line is not fixed to one state or one region. It shifts over plains, forests, lakes, mountains, and coastlines. Sometimes it lies far north and leaves much of the United States under broad warmth. Sometimes it drops southward and allows cold to spread deep into the continent. At this boundary, the meaning of season is often decided. Polar air carries the memory of low sun, long nights, snow cover, and ice-chilled ground. Subtropical air carries the memory of stronger sunlight, warm water, and abundant evaporation. When these two bodies of air approach one another, they do not merely exchange places, they create tension in the atmosphere, and that tension is one of the clearest ways seasons seem to collide. An air mass is a large body of air that takes on the temperature and moisture of the surface below it. Air that forms over snow and ice tends to become cold and dry. Air that forms over warm ocean water tends to become warm and moist. Once formed, an air mass can travel, but it does not lose its character immediately. This is why cold outbreaks can remain strikingly cold after moving southward for many hundreds of kilometers, and why warm humid flow from the Gulf can still feel distinctly southern far into the central United States. America lies in a place where these contrasting air masses often meet because the continent opens widely from north to south. There is no continuous east to west mountain wall to stop exchange across the interior. Cold can plunge south through the plains. Warmth can surge north through the same corridor. In winter and the colder shoulder seasons, dense cold air often gathers over Canada and the Arctic. Dense means heavier for its volume than the warmer air around it. Because cold air is denser, it tends to remain near the ground and spread outward when the larger circulation allows it. It can move southward as a shallow but powerful layer, undercutting warmer air ahead of it. At the surface, this arrival may be marked by a sharp wind shift, falling temperature, and a sudden hardening of the sky. Yet even as the cold air advances, warm, moist air may still continue to flow above or around it. The result is a vertical and horizontal overlap of seasonal states. Near the ground, winter reasserts itself, a little higher. The atmosphere may still carry the energy of spring or summer. This layering helps explain why the meeting of polar and subtropical air can produce such varied weather. If warm, moist air is forced to rise over advancing cold air, clouds thicken and precipitation develops. If temperatures remain below freezing through a deep enough layer, snow forms. If a shallow layer near the ground stays below freezing while warmer air exists above it, freezing rain or sleet may result. If the cold air retreats or arrives too late, this same system may produce heavy rain instead. Near these boundaries, a small change in wind direction or air temperature can alter the form of precipitation entirely. This is why transitional months often bring scenes that seem confused to human memory but remain consistent with atmospheric physics. The atmosphere is not indecisive. It is sorting competing air masses whose seasonal identities remain intact even as they overlap. The Great Plains are one of the most important settings for this meeting. From Texas northward into the Canadian prairies, the terrain is relatively open. Air masses can move across it with fewer barriers than in many other parts of the world. Cold, dry air can descend from the north. Warm, moist air can rise from the Gulf. Along the boundary between them, pressure falls, winds strengthen, and instability may grow. Instability means the tendency of air to keep rising once it has been lifted. When warm, moist air lies below colder air aloft, parcels of air can rise rapidly, helping thunderstorms develop. This is one reason spring across the central United States is not merely a gentle warming season. It is often a zone of atmospheric argument, where winter cold and summer-like moisture occupy the same broad region, and produce some of the continent's most dramatic contrasts. In the east, the meeting of these air masses is modified by the Atlantic coast, the Appalachian Mountains, and nearby warm water. In the west, mountain ranges and plateaus break up the motion of cold and warm air in different ways, sometimes trapping cold air in valleys while warmer air passes above. Yet across the country the same basic principle remains. Seasonal collision is strongest where unlike air masses remain sharply different and are brought together repeatedly. A warmer climate does not remove polar air from the system. The Arctic still produces cold and outbreaks still occur. What changes is the background into which that cold enters. Warmer average conditions, earlier spring warmth, higher humidity, and altered circulation can make the contrast feel even more abrupt when cold air returns. In daily life, this means a landscape already leaning toward one season can be pulled back toward another with striking speed. This contrast also affects severe weather. Tornado-producing storms, large hail, and damaging straight-line winds often develop where warm moist air meets colder. Drier air and strong winds change with height. Not every encounter between polar and subtropical air produces such events, but the ingredients often gather near the same boundary. This makes the collision of seasons more than a matter of discomfort or confusion. It can become a source of acute hazard. A week that begins with lingering frost may end with midsummer humidity and violent storms. The air masses themselves do not recognize seasonal labels, yet their encounters help create the human sense that the boundaries between the seasons are growing less orderly. Scientists are confident that the atmosphere is warming and carrying more moisture, and that these changes affect how warm air masses behave. It remains uncertain in some details how the frequency, depth, and pathway of particular cold air outbreaks will change from region to region because large-scale circulation, snow cover, sea ice, and natural variability all influence them. But observations clearly show that strong contrasts continue to occur, and when they occur within a warmer background, their consequences can feel more jarring. An early warm spell may trigger plant growth, insect activity, and human expectation, only for a later cold surge to damage crops, strain energy systems, and return the land to a winter-like state. The air masses do not just meet, they meet in a landscape already shifted by warming. From this region of direct atmospheric contact, the idea of seasons colliding becomes almost literal in physical terms. Cold northern air presses forward close to the ground. Warm southern air answers with moisture and buoyancy. Fronts sharpen, clouds build. Rain, snow, ice, thunder, and sudden temperature drops emerge from the struggle between them. The sequence of the year is still present, but it no longer always arrives as a smooth transition. Instead, the continent repeatedly becomes a boundary field where the memory of winter and the force of warmth occupy the same space. Here, in the meeting of polar air and subtropical heat, America's colliding seasons take on their most immediate and human form. At the surface of the continent, before roots, rivers, and cities fully enter the picture, the ground keeps its own seasonal record. Snow cover, frozen soil, and ice do not merely sit upon the land as passive remains of winter. They change how sunlight is handled, how heat moves, how water is stored, and how quickly the lower atmosphere can warm. In many parts of America, this white or frozen layer acts as a seasonal regulator. It reflects sunlight, insulates the earth below, slows evaporation, and preserves cold air near the surface. When that layer forms early, lasts long, or disappears abruptly, the timing of the year changes with it. As the climate warms, these surface conditions are shifting, and the shift helps explain why the boundary between seasons often feels less stable than it once did. Snow is one of the most effective reflectors in nature. Fresh snow can send a large share of incoming sunlight back upward, rather than allowing it to warm the ground. This reflectivity is called albedo. Albedo means the fraction of sunlight a surface reflects. Dark soil, wet pavement, forest canopy, and open water usually absorb much more energy than snow. Because of this, a snow-covered landscape tends to remain cooler than a snow-free one under the same sunlight. The difference can be large, especially in late winter and early spring, when the sun climbs higher and the days lengthen. If snow remains widespread, the land continues to behave in a winter-like way, even while the astronomical conditions move towards spring. If snow disappears early, the darker ground begins to absorb more energy at once, and warming at the surface can accelerate. This change in reflectivity creates one of the most important feedbacks in the seasonal system. A feedback is a process in which an initial change leads to further change in the same direction or in the opposite direction. In this case, when warming reduces snow cover, the darker land absorbs more sunlight, which can produce further warming and still faster snow loss. This does not happen evenly everywhere, and cloudy weather can slow it, but the basic physics is clear. The loss of snow removes one of the land's strongest winter protections against incoming solar energy. In many parts of the United States, especially in the north and at higher elevations, this means spring can gain momentum rapidly once snow retreats. Yet this does not guarantee a calm or permanent transition. A later cold intrusion can still arrive. The land may absorb sunlight like spring while the air briefly returns to winter. Frozen soil adds another layer to this surface story. Soil freezes when enough heat is lost from the ground and the water within it turns to ice. Frozen ground changes how water moves. Rain or meltwater may have trouble soaking in. Instead, more water can run across the surface. When late winter rain falls on frozen ground, or when rapid thaw follows snowmelt, the risk of runoff and flooding can increase. In this way, the collision of seasons is not only a matter of temperature, it is a matter of timing between frozen land and incoming moisture. The atmosphere may begin acting like spring, but the ground may still function like winter. This mismatch turns ordinary rain into floodwater and softens the border between the two seasons into a zone of strain. Snow also acts as insulation. A deep layer of snow traps air within it and can reduce the direct exchange of heat between the cold atmosphere and the soil beneath. This means the ground below thick snow may remain warmer than exposed ground during intense cold. If snow cover becomes thinner, patchier, or more variable, the insulating effect changes as well. Some places may experience deeper soil freezing during certain cold periods because the protective layer is absent. Even in a generally warmer climate, this is one reason seasonal change does not move in one simple direction. Average warming does not erase complexity, it redistributes it. Some winter processes weaken overall, yet short periods of exposure and refreezing can still become locally important. Across America, changes in snow cover are uneven. Mountain regions, northern forests, interior plains, and lake effect zones all respond differently. Temperature matters, but so do elevation, storm paths, humidity, and the supply of cold air. Observations indicate that snow cover duration has declined in many regions, and that spring snowmelt often occurs earlier than in the past. In lower elevation or marginal cold zones, warming can shift precipitation from snow toward rain more often. In colder places, heavy snow can still occur if moisture is abundant. What changes most clearly is the reliability of snow as a long-season boundary. Instead of persisting as a stable marker of winter, it more often fluctuates. It may arrive late, melt during warm spells, return briefly, and vanish early. This creates the impression of seasons interrupting one another, because the surface marker itself no longer follows a steady rhythm. Ice on lakes, rivers, and shallow waters contributes to the same pattern. Ice cover limits heat exchange between water and air. It also affects evaporation and local humidity. When ice forms later or breaks up earlier, more open water is exposed to wind and sunlight. That can alter local temperatures, cloud formation, and moisture supply. In northern states and around the Great Lakes, reduced ice cover can influence nearby weather by allowing greater evaporation in colder months and changing the seasonal lag between water and land. The result can be subtle at first glance, but it changes the local calendar of cold and thaw. Water bodies that once remained locked and quiet deeper into the season now sometimes release heat and moisture earlier, softening winter conditions in some moments while feeding cold season snowfall in others. The ground beneath snow and ice also remembers moisture. A wet spring following rapid melt can delay planting, soften roads, destabilize slopes, and shape early growing conditions. A dry winter with little snow can leave soils exposed and vulnerable to early warming, but it can also reduce water storage for later months. Snowpack in mountains is especially important because it serves as a seasonal reservoir. Water is stored as snow in the colder season and released gradually during melt. When more winter precipitation falls as rain rather than snow, or when snow melts earlier, that storage function weakens. Rivers may swell earlier and run lower later. In human experience, this means one season gives up its water to another at a different pace than before. Plants and animals respond closely to these surface cues. Snow disappearance exposes dark ground, emerging shoots, and nesting areas. Frozen ground delays root activity and microbial processes. Thaw opens pathways for water, nutrients, and movement. If snow retreats early, biological spring may begin sooner, but if a freeze returns, exposed tissues can be damaged. Here again, the surface condition becomes a mediator between atmospheric change and living consequence. The season at the ground may advance, then reverse, then advance again. What once seemed like a steadier progression becomes a broken sequence written in melt, refreeze, and exposed earth. Scientists are confident that warming is reducing snow cover and changing freeze-thaw patterns in many regions, especially at lower elevations and in the colder shoulder seasons. It remains uncertain how local snowpack, soil frost, and ice cover will evolve in every watershed and mountain range, because storms, topography, vegetation, and natural variability strongly influence them. But the broad physical pattern is well established. The white shield of winter is becoming less consistent. The frozen ground beneath it is meeting earlier warmth and shifting moisture in new combinations. This changes not only the temperature of a place, but the timing with which the land itself accepts the next season. From this surface region of snow, ice, and frozen earth, America's colliding seasons become visible in the land's own response to sunlight. The reflective cover of winter withdraws sooner in many places, exposing darker ground that warms quickly. Yet frozen layers can still remain below, and late cold can still return from above. Rain may fall onto soil that still behaves like ice. Spring may begin across a field while winter lingers just beneath it. In these changing surface states, the continent no longer shifts cleanly from one season to the next. It passes through a more fractured threshold, where the memory of winter and the onset of warmth occupy the same ground. The atmosphere and the broad energy of the seasons do not arrive over a flat and uniform continent. They cross a land of barriers, openings, basins, ridges, shorelines, and elevated plateaus. These physical forms do not create the seasons, but they shape how the seasons are felt, delayed, intensified, or mixed. Mountains lift air and force it to cool. Plains open corridors for rapid movement, Coasts admit the influence of nearby water, valleys trap cold. Deserts heat quickly under clear skies. Forests shade the soil and return moisture to the air. In America, the collision of seasons is therefore not spread evenly. It is filtered through landforms that give each region its own version of the changing year. To understand why seasonal disruption appears so varied across the country, it is necessary to remain at the scale of terrain and follow how the shape of the land reorganizes the air. The Western Mountains are one of the clearest examples. The Pacific sends air inland, but the first great obstacle it meets is a series of coastal ranges and then the higher chains farther east. When moist air is forced up a mountain slope, it expands and cools. Cooling encourages condensation, and condensation encourages cloud and precipitation. This process is called orographic lifting. Orographic means related to mountains. On the windward side, where air rises, clouds and precipitation often increase. On the leeward side, where air descends after crossing the crest, conditions often become drier and warmer. This creates sharp local climate contrasts across short distances. It also means that seasonal transitions do not move evenly from coast to interior. A storm that brings cold rain or snow to a western slope may leave a neighbouring basin dry and under clear sky. One region receives an extension of winter while another begins warming rapidly. Elevation adds another important difference. Higher ground is usually cooler because air pressure decreases with height, allowing rising air to expand and cool. Snow therefore lasts longer in mountains than in nearby lowlands. Spring at low elevation may already be established while nearby peaks still hold a deep winter character. Yet warming temperatures are changing the altitude at which snow can reliably form and persist. In some regions, the line between rain and snow is shifting upward. This creates a more unstable mountain shoulder season, with repeated swings between thaw and snowfall at middle elevations. The mountains still preserve cold, but they do so less evenly than before. A valley road may pass through green growth, wet earth, and flowing runoff while the slopes above remain white. Terrain turns one season into several stacked layers of time. East of the mountains, the interior plains form a very different environment. Here the land opens broadly from north to south. Without a continuous east to west mountain barrier, the plains allow large air masses to move with relative ease across long distances. This openness is one of the main reasons America experiences such dramatic seasonal contrasts. Cold air from Canada can descend quickly through the central corridor. Warm, moist air from the Gulf can surge northward through the same space. The land does little to block either flow. It therefore becomes a meeting ground where seasonal states are brought into direct contact. A calm spring day can shift rapidly as a front advances. A warm autumn stretch can be ended by a sudden polar outbreak. The plains do not soften the collision, they expose it. The Great Plains also influence storm development because warm air near the surface can rise beneath cooler air aloft, especially when the land heats strongly under spring and summer sunlight. Flat or gently rolling terrain allows heat to build over broad areas. At the same time, moisture moving northward from the Gulf often spreads widely across the lower atmosphere. Where these ingredients meet stronger winds and temperature contrasts, thunderstorms can organize and intensify. This does not happen because plains are empty. It happens because their openness allows large-scale gradients to remain intact over great distance. Seasonal boundaries are not diffused here. They are often sharpened. The geography helps preserve a broad contact zone between seasonal air masses. The eastern half of the country contains another kind of terrain influence. The Appalachian Mountains are lower than the Great Western Ranges, but they still redirect airflow, channel cold air into valleys, and create regional contrasts between windward and leeward slopes. Cold air can pool in valleys during clear nights. Cold pooling means dense chilled air settles into low places, where it may remain even after surrounding higher terrain begins to warm. This can delay local spring conditions or produce frost in places where daytime warmth has already encouraged growth. Along eastern slopes and interior basins, a region may look ready for a later season, while hidden low areas still behave like an earlier one. In this way, terrain creates pockets of seasonal resistance inside a larger warming trend. Coastlines bring a different form of control. Land heats and cools faster than water, so air near the ocean often moves inland by day and seaward by night, especially in fair weather. These sea and land breezes are local winds, but their seasonal effect can be meaningful. In spring, cool coastal water may delay inland warming close to shore. In autumn, the same water may release stored heat and keep nearby nights milder. Along the Pacific coast, marine influence can preserve a cool, cloudy feel while interior valleys heat quickly under stronger sun. Along the Atlantic and Gulf coasts, humid marine air can make spring feel advanced, even when inland areas remain more variable. Coasts therefore act as buffers, though not always gentle ones. When warm ocean water, humid air, and a nearby front combine, the coastal edge can become a place where seasonal contrast intensifies rather than softens. The Great Lakes form another terrain-like influence, though they are bodies of water rather than solid land. Their large surfaces store heat, delay freezing, and shape local wind and cloud patterns. Cold air crossing relatively warm lake water in the colder season can pick up moisture and produce heavy snowfall downwind. In warmer periods, the lakes can cool adjacent land and delay spring leaf out near shore. Ice cover, water temperature, and wind direction all affect these local seasonal lags. This means that even within a single state, one community may remain in a cool, delayed spring while another, farther from the lake, has already moved into fuller warmth. Large inland waters divide the seasonal map into smaller and less predictable pieces. Deserts and dry basins contribute another variation. Dry air and sparse vegetation allow strong daytime heating and rapid nighttime cooling. In such places, seasonal transitions can feel abrupt because the land responds quickly to changes in sunlight and cloud cover. A warm spell can develop suddenly under clear skies. A cold night can still follow if dry air and calm winds allow heat to escape after sunset. In the southwest, elevation changes across plateaus, mountains, and basins further complicate this pattern. Spring and autumn may not arrive as broad regional states, but as a patchwork of heat, cold air drainage, snow at elevation, and early dryness at lower levels. Terrain and aridity together produce a sharper edge to seasonal change. Scientists are confident that geography strongly controls local climate and weather, and that warming now interacts with these controls in regionally different ways. It remains uncertain in some places exactly how local wind patterns, snow lines, soil moisture, and storm behavior will shift at fine scales, because small terrain features can matter greatly. But the broad principle is well established. America's landforms do not merely decorate the seasonal cycle, they carve it into distinct regional expressions. As the atmosphere warms and moisture patterns shift, those regional expressions become more uneven. The same national season can appear early on one slope, late in one valley, humid on one coast, dry on one plateau, and violently unstable across an open plain. From this terrain-shaped region, the collision of seasons no longer appears as a single continental drama unfolding evenly from north to south. It appears as a mosaic. Mountains delay and divide, plains expose and accelerate, coasts buffer and moisten, valleys preserve cold, lakes stretch seasonal memory, deserts sharpen contrast. The continent receives the same turning year, yet its surface shapes transform that turning into many local calendars. In those layered calendars, one season may already be advancing while another still holds its ground a short distance away. The land itself ensures that America's seasons do not simply change, they fragment, overlap, and press against one another in place after place. Across the continent, one of the clearest changes in the seasonal year appears in the calendar itself. The names of the seasons remain the same, and the dates on the page remain the same. Yet the lived span of spring and summer is shifting. In many parts of the United States, warmth arrives earlier than it once did. Frost leaves sooner in the year. Plants begin growth earlier. Ice disappears earlier from rivers and lakes. Snowmelt often advances in time. Then, after the warmer months settle in, the return toward cooler conditions is often delayed. The result is not simply a hotter summer placed inside an unchanged year, it is a stretching and drifting of the warm part of the annual cycle. Spring begins to lean forward into what had once felt like late winter, and summer begins to extend its influence deeper into months that older memory often places nearer autumn. The shift does not happen everywhere in the same way. America is too large and too varied for one smooth national pattern. Coastal waters still delay warming in some places. Mountains still preserve snow at higher elevations. The far north still carries cold deep into the year. Yet broad observations across many regions show that the onset of spring conditions has advanced over recent decades. Earlier spring does not mean that every day is warm, or that late cold disappears. It means that the average timing of warming signals, especially those linked to biological and surface changes, often moves forward. Buds swell sooner, leaves unfold sooner, grass greens sooner, insects emerge sooner. These changes occur because the lower atmosphere and the ground reach key thresholds earlier than they once did. A threshold is a point at which a small additional change produces a clear transition. For plants, one threshold may be the accumulation of enough warmth to begin growth. For snowpack, another threshold may be the shift from regular freezing to regular melting. For people, the threshold may be the first sustained period without hard frost, or the first stretch of nights that no longer cool sharply. In a warming climate, many of these thresholds are crossed earlier. The process is often gradual in data, yet startling in lived experience. A season that once seemed to gather slowly may now appear to arrive before the land is fully prepared for it. The light of early spring is still soft and low, but the air may already hold unusual warmth. The year feels as though it is moving ahead of itself. This earlier spring has several layers. At the surface, snow retreats sooner in many places, exposing darker ground that absorbs more sunlight. In the lower atmosphere, warmer baseline temperatures make it easier for mild days to appear before the traditional heart of spring. In rivers and lakes, thaw and breakup often occur earlier. In ecosystems, the growing season often begins sooner. These changes reinforce one another. Exposed ground warms more easily. Earlier, plant growth alters moisture exchange with the air. Longer frost-free periods allow heat to accumulate across the season in a different way. Yet this advance is not the same as stability. An earlier spring can remain highly vulnerable to interruption. Warmth may arrive first, but a late freeze can still follow. That is one reason the new season feels colliding rather than simply shifted. The advance is real, but so is the risk of reversal. Summer, too, appears to be lengthening in many regions, though not as a uniform block of uninterrupted heat. What lengthens is the period during which summer-like conditions become more common. High temperatures arrive earlier in some places and persist later into the year. Nights remain warmer, humidity lingers. The atmosphere carries the sensory weight of midsummer deeper into the calendar. This does not mean that autumn disappears. It means the handoff becomes delayed and less decisive. The first cool periods of late summer or early autumn may no longer hold. Warmth returns after them. A landscape may begin to show the first hints of seasonal decline, while the air still feels firmly lodged in summer. Longer summers are influenced by several factors acting together. Warmer average temperatures raise the baseline from which heat waves develop. Warmer ocean waters nearby can delay seasonal cooling along coasts and feed humid air inland. Reduced snow cover in spring allows land surfaces in some regions to warm more quickly. Soil moisture also matters. Where soils dry out, more incoming solar energy goes into heating the air rather than evaporating water, which can intensify hot conditions. In cities, paved surfaces and built structures store heat and release it slowly, often keeping nights warmer than in surrounding rural areas. These different influences do not always line up in the same way, but together they support a longer period in which summer-like air dominates. The seasonal clock is also shifting in human terms. Agriculture adjusts planting dates. Allergy seasons begin earlier and last longer in many regions. Energy demand for cooling extends farther beyond the traditional center of summer. Outdoor labor, school schedules, recreation, and public health planning all begin to feel the drift. People notice not only hotter days, but a longer warm season surrounding them. The change is subtle at first because it is distributed across many small experiences. Then, over time, the accumulation becomes unmistakable. What once felt like a brief warming in April becomes repeated early heat. What once felt like a mild late September becomes oppressive warmth carried into October in some places. The season expands not through a single event, but through persistence. This extended warmth changes the emotional structure of the year as well. Spring has traditionally carried a sense of release from cold, a gradual opening of the landscape. Summer has carried fullness, ripeness, and long-established heat. When spring begins too early, that release can feel rushed. When summer begins before spring has settled, the intermediate phase grows thinner. When summer continues too long, the cooling expected later in the year becomes less reliable. In this way, the change is not only thermodynamic, it is temporal. The spacing between seasonal experiences begins to compress in one part of the year and stretch in another. The annual rhythm remains, but the intervals between its familiar notes are no longer the same. Observations strongly support earlier spring timing in many physical and biological indicators across the United States, along with a general increase in the length of the warm season in many regions. It remains uncertain how each local expression will evolve, because cold air outbreaks, cloud patterns, ocean variability, and terrain continue to shape local outcomes. Some places will still see abrupt reversals. Some high elevation or coastal regions will retain strong seasonal lag. But the larger direction is clear. America's warm season is encroaching on neighboring parts of the year. The advance is not smooth, and it is not complete, but it is substantial enough to shift both ecosystems and expectation. From this calendar region of earlier springs and longer summers, the collision of seasons appears not as a single violent overlap, but as a slow rearrangement of duration. Spring steps forward while winter still leaves traces behind. Summer expands outward while autumn waits longer to gain control. The year keeps its formal shape, yet the time given to each thermal phase is changing. Warmth enters sooner, settles earlier, and often remains later, in that stretched interval. America begins to live more of the year under summer's influence, and less under the clearer separations that once made the seasonal cycle feel steady and distinct. As the warm season lengthens across much of America, the cooler part of the year changes shape as well. Autumn does not vanish, and winter does not simply withdraw in one clean motion. Instead, the approach of cold becomes more uneven. In many regions, the lingering warmth of late summer holds on longer than older seasonal memory expects. Leaves may begin to change while the air still carries the heaviness of heat. Nights cool, then warm again. The first frost arrives later in many places, but when it comes, it may come abruptly after an extended mild spell. Winter then enters not always as a settled season of continuous cold, but increasingly as a season interrupted by gaps, thaws, and sharp reversals. This is one of the clearest ways the annual cycle begins to feel unstable. The descent into cold remains real, yet it often loses the steady pacing that once made autumn and winter feel distinct from one another. Autumn has always been a season of decline in sunlight. Day length shortens rapidly after the peak of summer. The sun lowers in the sky. The surface receives less energy with each passing week. This astronomical turning still proceeds with complete regularity. What changes is how long the atmosphere and the surface resist its cooling effect. Warmer oceans continue releasing stored summer heat. Soils and built surfaces remain warmer later into the year. In many parts of the country, especially where nearby water or persistent ridges support mild conditions, the atmosphere delays the onset of sustained autumn chill. The calendar advances, but the thermal season lags behind it. This creates one of the defining sensations of seasonal collision. The visual signs of autumn begin to appear while the air still behaves as though summer is not finished. The later arrival of frost is one of the most practical signs of this delay. Frost forms when surfaces cool enough for water vapor to deposit as ice, or for liquid droplets to freeze. Clear skies, light winds, dry air, and long nights often help this happen. In many regions of the United States, the average date of first frost has moved later over time. This extends the frost-free season, which is the span between the last spring frost and the first autumn frost. A longer frost-free season affects crops, gardens, insects, allergy timing, and ecosystem behavior. Yet a later first frost does not always mean a gentle autumn. It can mean weeks of extended mildness, followed by a sudden cold surge that catches landscapes and living systems after a longer delay. The transition grows less gradual even while it grows later. This delayed cooling can change autumn precipitation as well. Warmer air holds more moisture, and warmer nearby waters can continue feeding humid conditions into the season. In the east and south, this may allow heavy rain events to occur later into the year. Along some coasts, tropical moisture can remain influential well into months once associated more clearly with drier and cooler air in the west. Extended autumn warmth can delay the return of mountain snow at some elevations and prolong dry conditions in landscapes already stressed by summer heat. The seasonal meaning of autumn begins to split. It remains the season of declining light, but it may no longer consistently deliver early cool stability. Instead, it becomes a fluctuating interval in which summer warmth lingers. Moisture remains active, and winter waits at the edge before arriving more suddenly. Winter then enters a climate that is warmer on average than in the past, but not emptied of cold. This is an important distinction. The colder season still produces freezing air, snow, ice, and hard storms. Yet in many places, especially outside the far north and highest elevations. Winter increasingly contains interruptions. These interruptions may be warm spells lasting several days, rain falling where snow might once have fallen, or thaw events that briefly dissolve the settled appearance of the season. A thaw is a period in which temperatures rise enough to melt snow and soften frozen ground. Thaws are not new. They have always been part of many regional winters. What changes is their frequency, timing, and cumulative effect. Winter begins to feel less like one continuous state, and more like a season repeatedly broken open by intrusions from outside itself. This interruption matters because many winter processes depend on persistence. Snow cover needs sustained cold to build and remain. Lake and river ice needs consistent freezing conditions to form and thicken. Dormancy in plants and overwintering behavior in insects and animals depend not simply on cold occurring, but on cold remaining within expected bounds. Human systems also depend on winter persistence in subtle ways. Water managers rely on mountain snowpack as a stored reservoir. Transportation systems prepare for certain kinds of snow and ice risk. Buildings, roads, and energy systems are designed around established seasonal patterns when winter becomes patchier. These systems do not simply experience less winter, they experience a more erratic version of it, with freeze and thaw alternating in ways that strain materials, timing, and expectation. A freeze-thaw cycle is one example of this instability. Water enters cracks in soil, roads, and rock. It freezes, expands, then melts. Repeated cycles can weaken surfaces and damage infrastructure. In ecosystems, thawing followed by renewed freezing can expose roots or disturb organisms adapted to steadier snow cover. In agriculture, fruit trees and other plants may lose some winter protection during warm spells, becoming more vulnerable if severe cold returns. The issue is not that cold disappears, but that it is less consistently buffered by the same seasonal structure that once surrounded it. Winter gaps can therefore increase certain risks even as average winter temperatures rise. The character of snowfall changes under this pattern as well. In marginal temperature zones, warmer winters mean more precipitation falls as rain rather than snow. But when cold air does arrive, especially into a moist atmosphere, heavy snow can still occur. This creates an uneven winter identity. Long stretches may feel mild and wet, then a single strong storm can briefly restore a deep winter appearance. Snow may arrive later, melt sooner, and return in shorter intense episodes rather than as a long season of steady cover. For many people, this makes winter feel less reliable and more abrupt. It is present, then absent, then present again. The familiar continuity gives way to fragmentation. Observations across much of the United States support later first frosts, warmer autumn conditions in many regions, shorter snow seasons in many lower elevation areas, and more winter precipitation falling as rain in places near the freezing threshold. It remains uncertain how every local winter signal will evolve, because atmospheric circulation, snow feedbacks, ocean influence, and topography all continue to shape regional outcomes. Some regions will still experience severe cold and deep snow. Some winters will still arrive early or remain persistent, but the larger pattern is well established. The cooler half of the year is not only warming, it is becoming less even in its expression. From this region of delayed autumn and interrupted winter, America's colliding seasons take on a temporal form that feels especially intimate. Summer holds on after the light has begun to fade, autumn stretches but does not always settle. Frost waits longer, then strikes. Winter arrives in fragments, with gaps of rain, thaw, and soft air between colder episodes. The cold season no longer always descends as a long, steady occupation of the land. It often advances, retreats, and returns. In that broken movement, the boundaries between the seasons become harder to trust. The year still turns toward darkness and cold, but it does so with more hesitation, more interruption, and more overlap than before. When seasons begin to overlap, the result is not only a change in mood or timing, it becomes a change in hazard. Dry heat can build where spring rain once arrived more reliably. Heavy rain can fall onto landscapes hardened by drought or scarred by fire. A late cold spell can follow early growth. Warm water and moist air can feed flooding, while nearby regions remain locked in heat and smoke. These are compound extremes, meaning damaging conditions that occur together, follow one another closely, or interact in ways that increase harm. In America, the collision of seasons increasingly appears through these combinations. The atmosphere does not deliver one isolated signal at a time. It layers heat, moisture, dryness, wind, and sudden reversal into the same stretch of the year. Fire is one of the clearest examples. Wildfire depends on fuel, weather, and ignition. Fuel means the living and dead plant material that can burn. When winters are shorter or less snowy in some western and northern landscapes, the period between snowmelt and dry summer conditions can lengthen. Earlier spring warmth can bring earlier drying of grasses and shrubs in some regions, especially where soil moisture is limited. Long hot periods can remove more water from vegetation and soil. Wind can then turn a dry landscape into a fast-moving fire environment. None of these ingredients are entirely new. Fire has always been part of many American ecosystems. What changes is the timing, scale, and overlap of the conditions that support severe fire. A landscape may move from spring growth into summer-like dryness before the traditional calendar suggests it should. This does not mean every place becomes uniformly drier. In some regions, especially those influenced by changing storm tracks or warm nearby waters, intense rainfall events are increasing even while dry periods between them also lengthen. That combination matters because heavy rain does not always erase drought. If dry soil has become hard or water repellent, rainfall may run off quickly instead of soaking in. If a burned slope has lost vegetation and surface structure, a storm can trigger mudflows and flash floods rather than recovery. In this way, fire and flood can belong to the sesim-altered seasonal system. One season dries and heats the land more strongly. Another arrives not as a gentle wetting, but as a burst of intense rain. The result is not balance, it is sequential strain. Drought itself is more than a shortage of rain. It is a shortage of available water relative to need. Higher temperatures increase evaporation from soil and water surfaces and increase water loss from plants. This means that even where rainfall totals change little, warmer conditions can deepen dryness. In agriculture, this affects crop stress and irrigation demand. In forests, it weakens trees and can increase vulnerability to insects and disease. In rivers and reservoirs, it changes supply timing and storage pressure. When drought persists into what should be a replenishing season, people begin to feel that the year is no longer resetting itself. Spring may arrive in light and temperature, but not in moisture. The season appears by one measure and fails by another. Flooding shows the opposite side of the same instability. A warmer atmosphere can hold more water vapor, and when strong lifting occurs, storms can release that moisture in intense bursts. Flooding risk rises when such rain falls over saturated ground, frozen soil, urban surfaces, steep terrain, or snowpack that is already melting. In many parts of America, especially in transitional seasons, these ingredients can coincide. Rain on snow is one example. Warm rain falling on an existing snowpack can accelerate melt while adding water directly to rivers and streams. If the ground beneath remains frozen or saturated, runoff increases quickly. The event is not simply winter or spring, it is both at once. Snow remains from the cold season, but the atmosphere behaves like a warmer one. The river receives the combined force of both. Heat waves are also changing in ways that deepen seasonal collision. A heat wave is a sustained period of unusually high temperature for a given place and time of year. In a warming climate, heat waves are becoming more frequent, more intense, and longer in many regions. What matters for the seasonal story is that they can now arrive earlier in the year or persist later into it. An early season heat wave can be especially dangerous because people, ecosystems, and infrastructure may not yet be adapted to sustained high temperatures. Buildings may not be fully prepared for cooling demand. Workers may not be acclimated. Plants may still be in vulnerable growth stages. The heat belongs thermally to summer, but it may arrive during what the broader landscape still experiences as spring. This is one of the most direct forms of seasonal overlap. Severe storms add another layer. The central and eastern United States often experience dangerous thunderstorms where warm, moist air meets cooler, drier air, and strong wind changes with height. When warm, humid conditions arrive early or linger late, the seasonal window supportive of severe storms can shift or expand in some settings. Scientists continue to study how these storm environments are changing regionally, and uncertainty remains in the exact trends of tornado occurrence at local scales. But there is strong evidence that the ingredients for intense rainfall and certain forms of storm energy are affected by warming and added moisture. This means a spring already shaped by early warmth can still produce explosive storm conditions when colder air intrudes. The atmosphere does not choose one season's behavior, it combines them. The human experience of compound extremes is often defined by sequence. A warm winter reduces snowpack. Spring arrives early. Vegetation grows. A late freeze damages it. Summer heat follows quickly, drying the weakened landscape. Fire risk rises. Then a strong autumn rain falls on burned terrain and produces debris flows. Each event belongs partly to a different seasonal pattern, yet the boundaries between them have narrowed. Recovery time shrinks. Systems designed for one hazard meet another before they have reset. This is why colliding seasons feel exhausting to communities. The issue is not a single dramatic event alone. It is the compression of different types of stress into the same year, sometimes into the same month. Cities experience these overlaps in their own way. Hot pavement and buildings intensify heat. Impermeable surfaces increase runoff during heavy rain. Smoke from distant fires degrades air quality far from the flames. Power systems face rising cooling demand during prolonged warmth and storm damage during intense weather. Public health systems confront heat illness, flood-related contamination, respiratory effects from smoke, and stress from repeated disruption. What once seemed like separate seasonal problems become linked. Fire season reaches into months once considered spring. Flood season appears during warm periods. Heat persists into autumn. The urban year grows more crowded with risk. Scientists are confident that climate change is increasing the likelihood or severity of many heat extremes, heavy precipitation events, and drought-related stresses in the United States, and that wildfire conditions are worsening in many regions due to warming and drying. It remains uncertain exactly how every compound event will evolve region by region, because land management, ignition sources, local hydrology, and atmospheric variability all matter, but the broad pattern is clear. The hazards associated with different seasons are increasingly overlapping and interacting rather than remaining neatly separated in time. From this region of fire, flood, drought, and storm, America's colliding seasons become impossible to treat as a matter of perception alone. The overlap produces physical consequences. Heat dries fuels while rain later overwhelms hardened ground. Early warmth invites growth that later cold can injure. Moist air feeds floods while nearby landscapes burn. The year no longer spaces its dangers as clearly as it once did. Instead, the hazards of one season increasingly arrive before the last ones have finished. In that compression, the shifting climate reveals itself not only in altered weather, but in the stacking of extremes across a country asked to endure several seasonal threats at once. Beyond the atmosphere, beyond snow, water, and shifting hazard, the changing seasons enter living systems. Plants, animals, fungi, insects, and microbes do not read the calendar. They respond to cues: light, temperature, moisture, frost, snow cover, and the timing of food all help tell a living system where it stands in the year. In a stable seasonal pattern, these cues often align well enough for growth, migration, flowering, nesting, pollination, and dormancy to occur in a familiar sequence. In America, that sequence is becoming less even. Warmth may arrive early while daylight still matches an earlier season. Flowers may open before their usual pollinators are active. Migrating birds may return to landscapes whose food supply has shifted in time. Rivers may warm or swell earlier than the life cycles around them once expected. The collision of seasons is therefore not only a physical change in the sky and ground, it is a biological change in timing. This timing is often described through the word phenology. Phenology means the seasonal timing of recurring biological events, such as leaf out, flowering, insect emergence, bird migration, breeding, and autumn color change. It is one of the most sensitive ways to observe changing seasons because living things respond to small but important shifts in heat and moisture. Across many parts of the United States, spring phenology has moved earlier. Leaves emerge sooner, blossoms open sooner. Pollen seasons often begin earlier and can last longer. These changes are not uniform across all species or all regions. Some plants respond mostly to temperature. Some respond more strongly to day length, which does not change with climate warming. Some respond to winter chilling requirements, meaning they need a certain amount of cold before spring growth can begin normally. This difference in response is one reason ecosystems can slip out of step. A mismatch occurs when connected species respond to different cues and therefore change timing at different rates. A flowering plant may bloom earlier after a warm spell, while the insects that pollinate it may not emerge at exactly the same time. A bird may migrate according to day length and arrive on a familiar schedule, while the peak of the insects it feeds on has already passed. A stream may warm earlier, changing the timing of aquatic life, while the broader watershed still carries late cold runoff from snowmelt or a delayed storm. These mismatches do not always lead to collapse. Many species have flexibility. Some adjust their timing, range, or behavior. But the growing risk is that a system built around recurring seasonal coordination begins to lose some of that coordination. The year still turns, yet the cues no longer arrive in their old arrangement. Forests provide one of the clearest examples. In deciduous forests, many trees open leaves in spring after enough warmth accumulates. Earlier leaf out means the forest canopy closes sooner and begins exchanging water and carbon with the atmosphere earlier in the year. This can lengthen the growing season, It can also expose new leaves and flowers to harm if a late freeze follows. A freeze after leaf out can damage tissues, reduce growth, and alter the food available to insects and herbivores. In autumn, warmer conditions can delay colour change and leaf fall in some places, but drought stress can complicate that pattern. A forest may begin the year early, suffer interruption, then carry late warmth into a delayed decline. The biological season no longer maps neatly onto the old thermal sequence. Grasslands and agricultural landscapes show similar changes, though often with different consequences. Earlier warmth may begin growth sooner, but if rainfall does not arrive with it, soils may dry and stress may build quickly. Pollinators may become active at different times. Pest insects may expand their active season or survive winter more easily in some regions. Livestock and crops may experience heat stress earlier in the year or for longer periods. A field that looks seasonally advanced in green colour may still remain vulnerable to frost because the broader atmospheric pattern has not settled. This is one of the most striking features of colliding seasons in living systems. Biological spring may begin before climatic stability does. Migration reveals another layer of this disruption. Many birds travel great distances and time their movement using a mixture of day length, inherited patterns, weather signals, and food availability. If warming changes the timing of plant growth or insect abundance at breeding grounds, birds that arrive on older schedules may find altered conditions. Some species adjust, others do not adjust as quickly. Marine and freshwater species also experience shifting timing. Fish migrations, spawning, and food webs respond to water temperature, stream flow, snowmelt timing, and coastal conditions. When rivers peak earlier due to earlier snowmelt, or when warm spells and heavy rain alter flow patterns, the living rhythms tied to those waters change as well. Insects are especially sensitive to seasonal temperature. Many insects develop faster in warmer conditions, begin activity earlier, or extend their active period later into the year. This can alter pollination, pest pressure, and disease transmission. It can also change food availability for birds, amphibians, and other animals. But earlier insect emergence is not always beneficial to the insects themselves. A warm spell may trigger activity that is then followed by a hard freeze. A species may emerge into a landscape where host plants are not yet ready, or where dry conditions quickly reduce survival. As with other parts of the living system, the issue is not simply warming, it is the growing instability of the sequence. In the far north and at higher elevations, seasonal snow and ice remain important biological signals. Species adapted to long snow cover can be exposed when snow melts early or becomes patchy. Animals that rely on camouflage against snow may become more visible when white coats remain but the ground turns brown. Soil organisms and plant roots may face more frequent freeze-thaw cycles if insulating snow becomes unreliable. Wetlands may fill earlier or dry sooner. Amphibians may breed in ponds whose seasonal timing has shifted. The loss of a consistent winter surface changes not only temperature, but habitat itself. Living systems also contain memory. Seeds wait in soil. Trees carry stored energy from one year into the next. Animal populations reflect not just one season, but a series of seasons. Because of this, the biological effects of colliding seasons can accumulate. One early spring followed by a freeze may reduce fruit set. A longer hot season may then increase drought stress. A later warm autumn may alter migration timing. The consequence is not always immediate or dramatic in a single year, but over time the rhythm of reproduction, survival, and competition begins to shift. Some species expand their ranges, others retreat. Community composition changes. The identity of a place slowly adjusts to a different seasonal order. Scientists are confident that many biological indicators across the United States show earlier spring timing, longer growing seasons in many regions, and shifts in migration, flowering, and species ranges consistent with climate warming. It remains uncertain how every ecological relationship will respond, because species differ in flexibility and local environments differ greatly. Some systems may absorb change for a time, others may reorganize more quickly, but the broad pattern is clear. The cues that living things use to tell one season from another are becoming less synchronized. From this region of forests, fields, rivers, insects, and migrations, America's colliding seasons are revealed as a change in rhythm. Buds open before the danger of frost has fully passed. Pollinators and flowers negotiate a shifting timetable. Birds return to altered springs. Warmth stretches the growing season, yet stability does not always stretch with it. The land remains alive with recurring cycles, but those cycles no longer align as cleanly as before. In the living fabric of the continent, the boundaries between seasons blur into a new pattern of early beginnings, delayed endings, and uncertain coordination. When changing seasons reach human systems, they become visible in work, shelter, food, water, health, and routine. The atmosphere may shift in broad patterns, and forests may answer in leaves and bloom, but people experience the same transformation through planting dates, flood warnings, power bills, smoky skies, damaged roads, and nights that no longer cool as expected. In America, the collision of seasons enters daily life through systems built around older assumptions about timing. Crops are planted with an expected last frost in mind. Reservoirs are managed with an expected snowmelt season in mind. Roads, bridges, drainage pipes, and power lines are designed for expected freeze-thaw cycles, expected heat, and expected storms. As the seasonal year grows less steady, these expectations are tested more often. The meaning of colliding seasons at the human level is not only that weather feels strange, it is that the practical calendar of life becomes harder to trust. Agriculture shows this clearly. Farming depends on the sequence of warmth, cold, moisture, and sunlight more than on any single day of weather. Seeds need suitable soil temperature and moisture. Young plants need a reasonable chance of avoiding frost. Pollination needs seasonal coordination between crop development and insect activity or wind timing. Harvest depends on the pace of heat, rain, and drying through late summer and autumn. When spring arrives earlier in temperature but remains vulnerable to sudden cold, farmers face a difficult choice. Plant early to take advantage of warmth and a longer growing season, or wait because a late freeze can still destroy tender growth. Neither choice is simple. The season appears to open sooner, but the old risks remain partly alive within it. This uncertainty is especially difficult for fruit trees and other perennial crops. Many such plants respond quickly to warm spells after winter chilling needs have been met. Buds swell, blossoms open. The landscape looks committed to spring. Yet if a strong cold outbreak follows, flowers and young fruit can be badly damaged. The economic loss can be severe even if the rest of the year turns warm. In this way, colliding seasons do not only change averages, they magnify vulnerability at critical moments. A warmer spring is not always a safer spring. It can be a spring in which biological development moves ahead of the last reliable protection against cold. Water management faces a similar challenge. In the western United States, mountain snowpack has long served as a natural reservoir. Water is stored in solid form during the cold season and released gradually during melt. Cities, farms, ecosystems, and hydropower systems all depend on the timing of that release. When more winter precipitation falls as rain instead of snow, or when snow melts earlier, the annual flow of water shifts forward. Rivers may rise earlier in the year and run lower later in the dry season. Reservoir operators must balance flood control, summer supply, ecological needs, and electricity production under conditions that are less predictable than before. The season still turns from cold to warm, but the storage function once provided by winter is weakened or rearranged. In the central and eastern parts of the country, heavier rainfall and shifting storm timing place stress on drainage systems, levees, roads, and homes. Many urban and suburban systems were designed using rainfall expectations based on older climate conditions. When intense downpours become more common, water can exceed drainage capacity, flood streets, overwhelm basements, and contaminate water systems. If such rain falls during a season once thought relatively moderate, the disruption can feel especially disorienting. Spring may bring not only renewal, but flood cleanup. Autumn may bring not only cooling, but lingering tropical moisture and damaging rain. The infrastructure remains in place, but the seasonal envelope surrounding it has changed. Heat is another major pressure. In many cities, the built environment stores warmth in concrete, asphalt, brick, and roofing. These materials absorb solar energy during the day and release it slowly at night. This creates what is called the urban heat island effect, meaning cities often remain warmer than surrounding rural areas, especially after sunset. When summer-like heat arrives earlier or persists later, urban populations are exposed for longer periods. Warm nights are especially important because they reduce recovery from daytime heat. Older adults, outdoor workers, children, and people without reliable cooling face greater health risk. Energy demand rises as air conditioning use extends farther across the year. The result is not merely a hotter summer, but a longer season of thermal strain on households and electrical systems. Public health reflects these seasonal shifts in many forms. Longer pollen seasons can worsen allergies and respiratory stress. Smoke from more frequent or larger wildfires can spread over long distances and reduce air quality far from the fire itself. Heavy rain and flooding can increase exposure to mold, contaminated water, and disruption of medical services. Heat can increase dehydration, heart strain, and occupational illness. Milder winters in some areas may also affect the range or activity period of disease-carrying insects and ticks, though regional outcomes vary and remain an area of ongoing study. What matters here is that the health burdens once associated with separate parts of the year are beginning to overlap. Heat, smoke, allergens, storm damage, and flood risk may no longer occupy clearly distinct seasons. Housing and transportation also reveal the cost of broken seasonal continuity. Repeated freeze-thaw cycles crack pavement and weaken roads. Sudden winter storms following warm spells catch communities less prepared. Long hot seasons increase wear on rail lines, power equipment, and building materials. Insurance systems face rising losses from flooding, fire, hail, wind, and temperature-related damage. Construction schedules shift. School calendars meet unusual heat in months once regarded as moderate. Recreation patterns change as snow seasons shorten in some mountain regions, and heat limits outdoor activity in others. Even cultural expectations begin to move. Activities once linked to a certain season no longer reliably match the weather surrounding them. The burden is not shared equally. Communities with fewer resources often have less capacity to adapt. Low-income households may struggle with cooling costs, flood repairs, or crop losses. Rural communities may face repeated disruption from drought, fire, and storm-damaged infrastructure, tribal communities, fishing communities, and regions closely tied to seasonal water and ecosystem cycles may experience the changes in especially direct ways. Workers whose labor depends on weather, including farm workers, construction crews, delivery workers, and emergency responders, often feel the altered season first and most intensely. The shifting year becomes a matter of exposure, income, and safety, not only discomfort. Yet people also adapt. Planting schedules change, crops and varieties shift, reservoir operations are revised, cities open cooling centres, update drainage plans, and reconsider building materials and tree cover. Health agencies improve heat alerts and smoke guidance. None of these responses fully restore the older seasonal order because the physical background continues to change. But they show that human systems are not passive. They respond, though often unevenly and under pressure. Adaptation becomes part of the new seasonal reality. Scientists are confident that climate change is affecting agriculture, water resources, infrastructure, health, and energy demand across the United States through warming, altered precipitation, earlier snowmelt, heavier downpours, and more frequent heat extremes. It remains uncertain how fast and how evenly communities will adapt, because economics, policy, geography, and social inequality all shape resilience. But the larger conclusion is clear. America's colliding seasons are not confined to weather maps or natural landscapes. They have entered the systems through which people organize ordinary life. From this human region of farms, reservoirs, roads, homes, and bodies, the changing seasons become practical and immediate. Spring offers warmth, but not always safety from frost. Winter stores less water in some mountains, even as rain grows heavier elsewhere. Summer heat reaches farther into the year and deeper into the night. Autumn may delay relief while infrastructure still waits for an older pattern. The annual cycle remains familiar in name, yet less reliable in function. In that growing mismatch between expectation and reality, the collision of seasons becomes a condition people must live inside, manage, and endure. At the innermost level of this subject, after the wide planetary setting, the shifting air, the ocean heat, the moisture, the storm tracks, the land surface, the living systems, and the human consequences, the question becomes one of understanding. What is known with confidence about America's seasons now? What remains uncertain? How the scientific picture is assembled without forcing more certainty than the evidence can support. In this final region, the moving parts of the year are not described as scenery or hazard, but as knowledge itself. The seasons are seen through measurements, long records, physical laws, and the limits that still remain in a changing system. The strongest foundation is simple and clear. Earth's tilt still causes the seasons. That has not changed. The distribution of sunlight through the year remains the basic clock behind spring, summer, autumn, and winter. Also clear is the fact that the climate system has warmed because human activities have increased the concentration of heat-trapping gases in the atmosphere. This warming is observed in air temperature, ocean heat content, melting ice, changing snow cover, rising sea level, and many biological and hydrological records across the United States. This warming is already altering the conditions through which the seasons are expressed. The evidence for that broad conclusion is strong. It is well supported that many parts of the United States now experience earlier spring onset in physical and biological indicators. Snow often melts earlier. Rivers often peak earlier where snowmelt is important. Leaf out and flowering have advanced in many regions and species. Frost-free seasons have lengthened in many places. It is also well supported that heat extremes are becoming more frequent and more intense in many regions, and that the warm season has lengthened in many parts of the country. Heavy precipitation events have increased in many areas, especially where a warmer atmosphere can carry more water vapor into storms. Ocean waters around North America have warmed, and the atmosphere generally holds more moisture than before. These are not isolated findings. They fit together within well-understood physical principles. The broad meaning of colliding seasons can therefore be stated with care. America's seasons are not disappearing as astronomical realities, but the climatic and ecological markers that once made their boundaries feel more stable are shifting in timing, strength, and overlap. Earlier warmth can arrive while late cold remains possible. Summer-like heat can extend later into the year. Winter can lose persistence in some regions even while severe cold outbreaks still occur. Snow can become less reliable as a seasonal boundary in many lower elevation and marginal cold regions. The hazards linked to different seasons can overlap more often. This interpretation is strongly supported by the combination of observed warming, moisture change, snow loss in many areas, shifting phenology, and the changing character of extremes. Scientific confidence is also high that regional differences matter greatly. America is not a single climate zone. Alaska, the desert Southwest, the Pacific Coast, the Great Plains, the Great Lakes region, the Southeast, the Northeast, and the Mountain West all respond differently because latitude, elevation, ocean influence, land cover, and water availability differ so strongly. What is true in broad direction across the country is not identical in local timing or local intensity. Some regions may experience stronger trends toward earlier springs. Others may show larger changes in heavy rainfall. Some mountain zones may still retain deep snow in cold years, while nearby lower elevations shift strongly toward rain. This regional variation is not a weakness in the science. It is part of the science. There are also questions that remain open or are still being refined. One of the most studied is how the warming Arctic influences the jet stream and middle latitude circulation. Observations indicate that Arctic warming is rapid, and that this may affect the temperature gradients shaping the upper atmosphere. Some studies suggest links to more persistent or amplified patterns in certain conditions. Other studies find that tropical influences internal variability, and other drivers may be equally or more important in many cases. The atmosphere is complex, and the exact contribution of each factor to every wavering pattern is still under investigation. The scientific position here is not ignorance. It is active inquiry within a system that has many interacting parts. A similar caution applies to some regional hazards. Scientists are confident that heavy rainfall environments and heat extremes are changing. They are confident that wildfire risk is increasing in many regions through warming and drying, though land management and ignition sources also matter strongly. But not every kind of extreme event shows the same level of certainty and trend at the local scale. Tornado records, for example, are influenced by changes in observation practices and clustering, and the regional future of severe convective storms remains an area of continuing research. Cold air outbreaks still occur, and while winters are warming overall, the precise future behavior of specific cold extremes depends on circulation, snow cover, and other variables. The responsible scientific approach is to separate robust signals from narrower, unresolved details. This is one reason long records matter. A single strange season can live in memory as proof of everything, but science depends on repeated measurement over time. Weather varies naturally from year to year. Climate is the longer pattern within which that variability occurs. To know whether seasons are shifting, researchers examine many decades of temperature, snowfall, sea surface conditions, stream flow, phenology, frost dates, satellite observations, and physical modelling. When many independent lines of evidence point in the same direction, confidence grows. When evidence diverges or remains sparse, uncertainty is stated. This method does not remove all doubt, it disciplines it. Models also play a role. A climate model is a mathematical representation of the atmosphere, oceans, land, and ice based on physical laws. Models are not crystal balls. They do not predict the exact weather on a given day many years ahead. What they do is help explore how the climate system responds to different levels of greenhouse gases, different ocean states, and different feedbacks. When models reproduce broad observed trends, and those trends align with physical understanding, they strengthen confidence in the larger picture. When models differ on regional details, scientists compare them, refine them, and remain careful in their conclusions. This is especially important for seasonal questions, because regional terrain, coastlines, snow processes, and storm tracks can produce differences that are difficult to resolve perfectly. What emerges from all this work is not a story of mystery without answer, nor a story of total certainty. It is a measured conclusion. America's seasons are changing in ways that are already observable and physically consistent with a warming climate. The most robust signs include earlier spring conditions in many systems, longer warm seasons in many regions, reduced snow and ice persistence in many lower or milder cold zones, more atmospheric moisture, heavier rainfall in many settings, and growing overlap among seasonal hazards. What remains less certain is the exact regional expression of some circulation shifts, the behavior of particular classes of extreme events in every locality, and the pace at which local ecosystems and communities will adapt. This measured understanding matters because it replaces confusion with proportion. It shows that the feeling of seasons colliding is not merely personal impression, yet it also avoids claiming that every unusual event proves a complete transformation. The year is still structured by sunlight and orbit. Winter still comes. Summer still comes. Spring and autumn still exist. But the climate background through which those seasons move has changed enough to alter their timing, their texture, and their boundaries. In some places the changes are subtle but cumulative. In others they are already stark. Across the country, the evidence points in one broad direction. The seasonal order that many people remember is not being erased all at once. It is being reshaped from within by a warmer atmosphere, warmer oceans, changing snow and moisture patterns, and the many responses that follow. At this innermost level, then, the meaning of colliding seasons becomes plain. It means that the old separators of the year are weakening in many parts of America, even while the basic celestial rhythm remains. It means that certainty is strongest about the warming background and the shifting patterns already visible in observation, and weaker about some finer details of circulation and regional extremes. It means that science can describe both change and uncertainty honestly at the same time. And it means that the country now lives within a seasonal system that is still familiar in name, still governed by the same planet and sun, yet increasingly altered in the way it unfolds from one part of the year into the next. The continent settles under the same turning sky that has guided every earlier year. Light still rises and falls in its measured order. The tilted Earth still offers its long familiar pattern of brightening and dimming, warmth and cooling, growth and rest. Yet across America, that old order now moves through air, water, ground, and living systems that no longer answer in quite the same way. Spring often stirs sooner, but not always safely. Summer often lingers longer, but not always gently. Autumn can delay its cooling. Winter can arrive in fragments, with cold still sharp but less continuous in many places. The seasons remain, though their edges soften, overlap, and shift. In this quieter view, the change does not appear as a sudden break with the past. It appears as a slow rearrangement of timing, contrast, and persistence. Warmth reaches farther. Snow retreats less reliably in many regions. Moisture gathers differently in the sky. Storms carry more of one season into the space of another. Forests, rivers, farms, cities, and coasts all register the altered rhythm in their own way. What was once a steadier sequence becomes a more uneven passage, with pauses, reversals, and compressed transitions. Still, the pattern is not without meaning. The science shows both what is clear and what remains unresolved. The broad direction is well known. The finer details continue to be studied. Beneath both certainty and uncertainty, the year goes on, not vanished, not replaced, but transformed in its expression. America's seasons now meet one another more closely than before, their signals mingling across the same landscapes, their boundaries less firm, their handoffs less calm. And under the steady motion of Earth around the sun, the continent continues through that altered cycle, one changing season leaning gently, and sometimes abruptly, into the next.